My name is Shijie Li. I will present our work, Dually Pyramid Generative Adversary Networks for Semantic Image Synthesis. This work is collaborated by Professor Mingming Cheng in Nankai University and Professor Yugen Gao in Bonn University. Generative adversary networks have become very successful in generating simple photorealistic images, like face or animals. However, it is still very challenging to generate images of complex things that contain many different objects at various scales. This is also the case when the semantic layout is provided, like for content generation or image editing. This task is also known as semantic image synthesis and requires to generate photorealistic images for given semantic input layout. One issue for previous methods is that they are struggling to generate realistic objects across different scales. For instance, large objects like trucks, buses, or trams are generated as collages of patches as shown in the first and second row, and small objects like traffic signs or borders fade away and barely recognizable as shown in the second and third row. This is due to previously methods usually cannot handle scale information in the generative and discriminator properly. In this work, we address this problem by properly dealing with different object sets in the generator and discriminator. Previously work usually conditioned each spatial adaptive normalization block statically on the resized label map, which usually causes details lost in the generated images. As comparison, our generator adapts the conditioning for each scale by a second pyramid. In this way, the conditioning is adaptive to the size of the objects, and artifacts of combining patches of different scales are avoided. This improves the quality of the generated objects both for small objects like things as well as large objects. While our generator is able to generate small objects, like borders, previously proposed classification-based or segmentation-based discriminators doesn't handle such small details in the label map, and thus do not encourage the generator to generate small objects. While classification-based discriminators ignore such details completely, the segmentation-based discriminators proposed doesn't handle scale information well, and extending the discriminator to different scales even deteriorates the quality of the generated images. To address this issue, we introduce supervision at different levels. We first introduce multi-scale adversary supervision at patch level. The laws ensure that important scale information is preserved within the discriminator, such that the generator is enforced to generate more realistic objects at various scales. Then, a segmentation-based supervision is introduced to provide pixel-level supervision, which offers precise supervision on generated content. The third one is a multi-scale feature matching loss. It encourages the generator to generate images that align with the input semantic maps at all scales. We show that the unification of the three types of supervision is essential to generate realistic objects that align with the semantic layout. For fair comparison, we also introduce label mix regularization into our work, which mixes the real data and the generated data by semantic mask. Here we show the full supervision to train our model, which includes all supervision mentioned before. We compare our method to the state-of-the-art method here. Our method achieves the best performance, measured by FID and mean-LU on all datasets. On cityscape datasets, our method outperforms previously state-of-the-art methods by 3.6 FID and 4.3 mean-LU. On the ADE20K datasets, our approach achieves an improvement by 2.2 FID and 3.9 mean-LU Only on the ADE20K outdoor dataset, the mean value of our approach is the same as previously state-of-the-art methods. This is not surprisingly, since the outdoor images contain less objects, and our method is try to generate photorealistic objects in complex scenes. Nevertheless, our approach achieves 2.8 FID compared to previously state-of-the-art methods, and thus generated more realistic images. In order to analyze the effect on object class and other semantic class more in detail, we report the pre-class IOU for cityscape datasets. Except for the class fin, the mean IOU for non-object classes is similar to the other approaches, but our approach achieves a much higher IOU for the object classes, in particular for the small object classes pole, traffic light, and sun, and the large object classes track, bus, and train. The improvements in IOU are by a very large margin. For all object classes, the mean IOU is improved by 5.4, which is higher than the improvement for all classes. Here we show the generated objects of different size. All these objects are cropped from the generated images on cityscape datasets. The objects on the left-hand side are generated by previously state-of-the-art methods, whereas the objects on the right-hand side are generated by our methods. We can observe our methods generate more realistic objects for all sizes. Here, we analyze the impact of the proposed generator and discriminator. To this end, we combine the proposed generator and discriminator with the generator and discriminator of previously state-of-the-art methods OILs. Replacing the discriminator of OILs by our discriminator substantially improves mean IOU by 4.7. For the object class, mean IOU even improves by 5.9 FID, however, doesn't significantly change. In contrast, replacing the generator of OILs with our generator substantially decreases FID by 2.3, but increases the mean IOU only slightly. This shows that the combination of the proposed generator and discriminator is essential to achieve a low FID and a high mean IOU. Below image illustrates the effect of the generator and the discriminator on the generated images. Next, we evaluate the impact of multi-scale adversary supervision. The first row shows the results without the loss. For the other rows, the loss is either added to the encoder or decoder of the discriminator or to both. Adding the loss improves FID and mean IOU. This shows that adding the loss to a segmentation-based discriminator improves the quality of the generated images substantially. The difference of adding the loss to the encoder, decoder, or both are smaller, but using it only for the encoder performs the best. Finally, we evaluate the impact of using feature alignment. While it doesn't improve the FID, the mean IOU improves by 3.7 if the feature matching loss is added to the decoder of the discriminator. In contrast, adding the feature matching loss to the encoder decreases the performance. For the decoder, it actually increased the performance. Here we show some qualitative analysis on ADE20K datasets. We can see that our approach performs well for both indoor and outdoor images. Previously state-of-the-art methods, SPAD and OILs, struggle to generate multi-instance of objects, like one of the chairs in the row 2 is either of poor quality or in the wrong direction, and the two beds in row 3 are connected. In contrast, our approach generates in all class realistic images. Apart from the quality of the generated images, the diversity is also very important for generative model. Here we show some images generated from our model with different noise. This denotes our methods can produce diverse images given the same semantic layout. Thanks for watching. The code and the data will be released soon.